a quick recap of what we did last time. We considered an RL circuit and we wrote down the differential equations of the RL circuit and obtained the response of this circuit and tried to understand the nature of the components of the response of a RL circuit, both the transient and the steady state. Now, the first kind of circuit we tried to study was a linear circuit in which the equation of an inductor is V, the voltage across it V is equal to L di by dt. And the other kind of circuit was where we considered a nonlinear inductor in which V is not equal to L di by dt, because the flux link in the coil is not a linear function of the current. As a result of which we get a nonlinear equation, and in case of a nonlinear equation we could not write down, we did not write down the response, because it is generally quite difficult to solve a nonlinear differential equation. What we did instead was did a numerical integration, and we saw some interesting effects that when a inductor enters or is in a nonlinear region, then you in fact have a quite a large inrush current. Incidentally, we tried to get the response of a linear inductor for two kinds of sources. One was a DC source and one was an AC source. So, just to recap quickly what we did, we recognize that the response of equation of this kind, a differential equation of this kind, has two components. One is e raised to at into x0, and this is the effect of the input. So, if we have a DC source, in that case the response turns out to be this, and if you actually evaluate it, you would have what we got essentially was this, and from this we could infer that the response, final response of the current is the natural response, which is obtained by doing that integration, which is obtained by solving the equation, and also a forced response. So, the response is in fact a function of both the initial conditions as well as the source which you have. In fact, in the case of sinusoidal input for a linear inductor, the response comes out to be this. Here too we have what is known as the forced response or the sinusoidal steady state response, and also one component here which is the natural response of the circuit. And one of the points which you should take into account is that although we have used a formula to obtain the natural response and the steady state response components of the current response, you will notice that if you evaluate this expression at time t is equal to 0, you will simply get the consistent solution, that is I of 0 is equal to I of 0. Because for example, here if you plug in t is equal to 0, you will get Vm by root of r square plus omega square L square into minus sin phi, and this at t is equal to 0 cancels with this, because at t is equal to 0 this is 1 and this is also 1. So, you will get I0 is equal to I0. So, this is a consistent kind of this the solution is correct in the sense that it is consistent with the initial conditions as well. Now, one of the important points is that in case current is actually defined by this differential equation, in fact the current can't change instantaneously. The reason being that this if current changes instantaneously, then this di by dt will become infinity. So, one of the in fact conditions which this solution satisfies, and that is why it is also a correct solution, I mean that shows it is it is consistent, is that the current before the disturbance and after the disturbance is equal. So, that is why I0 just after you switch on the switch, you will find that the current is equal to the initial condition. So, this is kind of a consistency check. You can also take the derivative of this expression and show that it actually satisfies this equation as well. So, this is something we did last time. just to write it down a bit. So, if you have got a DC source, what we have is the response is F1 plus F2, where F1 is the sinusoidal steady state response equal to V by R, sorry, not the sinusoid, the DC response, we are talking of DC here, and there is F2 is the natural response, and that is has the form e raised to minus R by L times T. So, your total response is actually I is equal to F1 plus F2. So, of course, this A, as we have seen before, A is nothing but I0 plus F1 evaluated at time t is equal to 0, sorry, minus. So, this is what we find here, and because of this you will notice that F1 plus F2 at time t is equal to 0 will be equal to I0. So, this is essentially the response we get for DC. In case we have got AC, let us say, so the input U is equal to V. In case the input U is equal to Vm sin omega t, the response is similarly given by F1 plus F2, where F1 is the steady state response, sinusoidal steady state response is Vm by root of R square plus omega square L square into sin omega t minus phi, where phi is equal to tan inverse omega L by R. And as before, we will get F2 is equal to, we will call this A sinusoidal e raised to minus R by L t, where As also will be I0 minus F1 of 0. So, you evaluate this at F1 of 0 multiplied by the minus sign, and this A will be this. So, this will ensure that your response is satisfies the equation as well as the initial condition. Now, if you have got an input which is slightly different, for example, Vm1 sin omega 1 t plus Vm2 sin omega 2 t plus alpha, suppose, then what is the forced response or the sinusoidal steady state response? The sinusoidal steady state response is given by Vm1, that is F1 will be equal to Vm1 by root of R square plus omega 1 square L square sin of omega 1 t minus phi 1, and Vm2 will be given by L square into sin omega 2 t plus alpha minus phi 2. So, this is something you can verify by actually evaluating the response using the formula which I had given for a differential equation, this one. So, you will get in fact this response in F2, which is going to be A e raised to minus R by L t, where A will be equal to I0 plus F1 sorry minus of F1 of 0. So, you have to evaluate this F1 at 0, and so we will get consistent and correct amplitudes of the natural response. So, the response is actually consisting of F1 plus F2. Now, what you notice here of course is you in fact have a superposition of the response is also a superposition of the individual responses corresponding to these components. So, F1 in fact the sinusoidal steady state response, if you have got two sinusoidal sources, you will get the steady state response to be the superimposition of the responses due to each individual component. Okay. The natural component, of course, natural response component of course has to be computed in this fashion here. So, this is essentially what we see here, and this actually follows from simply applying this. So, you will actually have two components, and if you apply this you will come to this conclusion. So, this is the response in case you have got two sinusoidal inputs. Interestingly, for DC and sinusoidal inputs, what you notice is that the steady state response or rather the response which remains after this dies down, the natural response dies down, is in fact of the same nature as the input. That is, for DC you get DC, for AC, that is sinusoidal input, you get a sinusoidal output. In case you have got a sum of sinusoids, you get corresponding outputs which are of the same waveform. Of course, the phase shifts and the scalings are different. In fact, here the scaling is dependent on omega 1 and omega 2, and phi 1 and phi 2 is equal to tan inverse, and phi 2 is equal to tan inverse omega 2 L by R. So, this is effectively the kind of responses you get. Remember that in case your inductor is nonlinear, we are not going to have this kind of situation. We saw yesterday that if you introduce a nonlinearity, the current waveforms in steady state are not sinusoidal. So, you in fact have got harmonics which are not present in the input, which appear in the final output. Okay. So, even in although you may have a periodic steady state, it may not be having the frequency components which are there in the input. So, there may be some additional frequency components leading to a non-sinusoidal waveform. So, an interesting thing is that you can superimpose the sinusoidal steady state responses caused by two different sources. In fact, another class of inputs preserves its wave shape. For example, if your input is e raised to st plus alpha, so instead of take the input as sin omega t, you take it as, or cos omega t for that matter. In fact, if you replace this by cos omega t, this will also be cos omega 1 t minus phi, and sin omega 2 will be sin omega t minus phi. If you add an alpha, it appears here also. So, this is something which is makes the analysis of the sinusoidal state quite straightforward. In fact, as I mentioned, another class of inputs or a more generalized form of what we have discussed so far is to consider an input e raised to st plus alpha. If you have got e raised to st plus alpha, the forced response here is equal to e raised to st plus alpha divided by R plus SL. So, in fact, you will find that the response is given by e raised to st plus alpha divided by R plus SL. In fact, if you put S is equal to 0, then you will get e raised to alpha, which is a constant, and in that case you will have e raised to alpha upon R, because S is equal to 0. In fact, that corresponds to the DC steady state response. You will simply get e raised to alpha divided by R if your input is e raised to alpha. So, this is a interesting thing. So, this is a more general way of writing down the response. In fact, if you you in fact take S is equal to j omega, then F1 will be e raised to j omega t plus alpha upon R plus j omega L. And in fact, you will notice that this is equal to e raised to j omega t plus alpha upon R square plus omega square L square into e raised to minus j phi, where phi is equal to tan inverse omega L by R. So, does this sound familiar? We have done this before. This is in fact giving you the same information as we had seen for the sinusoidal steady state response. So, in fact, putting S is, so you can treat e raised to st plus alpha as a generic DC or sinusoidal input, and we can easily infer what the input final output forced, or rather the sinusoidal steady state responses or the DC steady state responses by appropriately substituting for S is equal to j omega or S is equal to 0. So, this is an interesting application of complex numbers here, because the same information, that is a phase shift of phi and a scaling of R square plus omega square L square, is simply obtained by putting S is equal to j omega. So, this is a very kind of interesting way of representing the sinusoidal steady state. Interestingly, the root of this denominator is S is equal to minus S is equal to minus R by L is also the constant which appears in the exponent or the coefficient which appears in the exponent of the natural response. Remember, the natural response always has a magnitude A such that f1 plus f2, which is the correct and complete response, satisfies the initial condition. So, instead of actually working out what the entire response can be, you can first obtain in case of inputs which are DC or sinusoids or of this nature, directly get the forced response and then infer A from the fact that the initial conditions ought to be satisfied. So, this is a interesting trick which prevents you from which kind of relieves you of the burden of trying to do a very detailed integration and so on. Okay. So, the sinusoidal response can be got quite simply. If you have got a sinusoid of frequency omega, you will find that the same information, that there is a phase shift and a scaling, can be obtained simply by substituting S is equal to j omega. So, this is a interesting thing to do. So, we had considered a circuit with a source, and this is taken at t is equal to 0. This we assume here that the instant of switching is t is equal to 0 for convenience. So, and the initial condition is what is the current at t is equal to 0, but this is just for convenience. You can shift the time to adjust, you can have a switching at other instants. What is important is at what point of the, what is the value of the input at the point where you switch on this, and what are the initial conditions when you switch on this. Of course, if this was open all the time before you switch this, then the current initially will be 0. But you can have circuits where there is some initial current circulating in the inductor when you switch this. Okay. This is of course not possible here, but it could be, for example, true in a situation or a circuit like this, where there could be an initial condition prior to this being switched on. But let us not consider a detail, we can understand more complicated circuits later, but in your, especially in your assignments, we could consider slightly more complicated circuits, but this is a simple example. In fact, you can look at it as if you have got a kind of, we call it the impedance, and that is R plus SL is the impedance, and if input is V, then V upon R plus SL denotes the response. So, V is nothing but something of the form, of course, we could always multiply this by some k, and most of our what we said would still be true. For example, this would still be, if this was k, this would be k, and this would be k, and this would be k. So, this does not really affect the, also as I mentioned some time back, in the sinusoidal steady state response, you could actually apply superposition, provided that the inductance is linear. Okay. So, in fact, if you have got an input like this, your response can be written down as V plus SL, and of course, with the usual meaning that in case it is a sinusoid, then you have to substitute S is equal to j omega and get phi and R square plus omega square L square from there. So, this is a neat way of doing it, where we replace the inductor by SL. So, in fact, it is not surprising because the voltage across the inductor, I will call this VL, the voltage across the inductor satisfies the equation L di by dt, and so what you effectively see is that if VL has got, if IL is I e raised to s t plus alpha minus phi, suppose, in that case your voltage will be L into I into S. So, what you will find is the voltage is this, because if you take the derivative of this, S will come out, S would in fact e raised to st, when you take the derivative, is s e raised to st. So, it is not surprising that the inductor voltage is related to the current by this SL. So, what we can do is, in more complicated circuits also, we can actually obtain the what is known as the impedance and quite easily get the steady state response. For example, if you take now a slightly more complicated circuit, which is a RLC circuit, and apply a step to it. So, if you take a RLC and give it a DC step, can we just see the, yes. Now, we have got a slightly more complicated circuit where you got RLC, and in case you write down the differential equations of this circuit, you will find that if you apply KVL for this circuit. So, I will just do this. So, what we will get is now we have got a DC and an R, an L and C. This is R, L and C. So, what are the differential equations of this? Let us say this is switched on at t is equal to 0. So, you will have first you can write a differential equation for the current. L di by dt, let us assume it is a linear inductor, is the voltage drop across this. So, V, if this is the input V, minus L di by dt minus IR, which is the drop here, then the drop here, and this is Vc is equal to 0, sorry, minus Vc is equal to 0, and also C dVc by dt is equal to I. So, these are in fact now two differential equations. So, we have got now a set of coupled differential equations, and to solve this it does not take much to do this. In fact, what we can do is consider, if you have got a voltage here, this you can consider this as SL and SC, okay, 1 upon SC. So, what do I mean by this? That in case in case of a capacitor, I and V are reversed. So, what you will find is that what I did just now for the inductor, Vc into SC is equal to I. So, this is the kind of relationship between the current and the voltage. In case we assume that in steady state the nature of I and V are e raised to st plus alpha. So, what really happens is that Vc can be written as I upon Sc. With this is all with the assumption, this entire thing is with the assumption that your input is e raised to st plus alpha, and this of course pertains to the steady state. Okay. So, what you get is SL here and 1 upon Sc here, and if you want to find out the response of this circuit in steady state, you have to just put V is equal to R plus 1 upon Sc plus SL. So, since it is a series circuit, that is what we will get. So, it becomes like almost like an algebraic equation, but the understanding here of course is this is the sinusoidal steady state response, sinusoidal response, where V is equal to e raised to st plus alpha, or k into e raised to st plus alpha. Now, in case it is a DC source, S is equal to 0. So, what you will find that the current in steady state is simply will be equal to V upon R plus 1 upon Sc plus SL. If you put S is equal to 0, this will become equal to 0, because the thing is that Sc will be tending to infinity. So, what you find is that in this circuit the DC steady state current is simply obtained by plugging in S is equal to 0. This will give you the DC steady state. Interestingly enough, here also you will have a natural response, and as before I told you, the roots of the denominator of this equation, surprisingly enough, give you some idea of how the natural response of this circuit is going to be. In case of the RL circuit, we had something like this. So, if V is an input e raised to st plus alpha, this is the steady state output. In case you have got an RL circuit, the steady state output is this. So, what you find is that the denominator of this, if you set it to 0 and find out the value of S which results in this turned out to be the thing which came in the exponent of the natural response. So, in fact, this is true even now. I mean, we do not prove it here. You can do a rigorous solution of this circuit using the mathematical formulae related to so called eigenvalues and eigenvectors. But what interesting thing which comes out quite easily here, which does not require all this, is you take the denominator of this and set it equal to 0. This is also called the characteristic equation. So, what you will find is the natural response. Now, please remember that the steady state response, in case you have got an input k, that is V is equal to k e raised to st plus alpha, is in fact this. This is the steady state response. The natural response has got components not minus r by L e raised to minus r by L t, but something else. And how this is actually obtained is simply by setting this equal to 0, and if you do that, you will find that S square L c plus SCR plus 1 is equal to 0, and you will have to find out the roots of this. So, for example, in case your R is equal to 10 ohm, L is equal to 63.32 millihenry, and C is equal to 10 microfarad, it turns out that the roots of this are, I will call it S is equal to, in fact there are two roots for this, and they turn out to be complex, 96 plus J 1254.21. So, plus or minus. So, there are two roots which are complex, having a real part and an imaginary part. Now, please remember what I am trying to say here. If you have got this circuit, there are two components of this response. This, of course, V could be anything. I have just shown it AC here, but it could be anything. Let us just say it is V. There are two components, F1 plus F2 for the current. F1 is obtained if V, the input is V is equal to k e raised to st plus alpha, the output is V plus R plus 1 by Sc plus Sl, that is equal to k e raised to st plus alpha. Remember, for a linear circuit the nature of the response remains the same, but everything is scaled. Okay. So, this is F1. So, this is the current. In fact, the first component of it is what is known as the steady state response is simply going to be F1, whereas F2 in this case has some interesting features. In fact, F2 will have the nature A1 e raised to lambda 1 t plus A2 e raised to lambda 2 t. This is what is known as a second order circuit. So, actually we get two parts to this natural response, and interestingly this what you notice here is that this lambda 1 and lambda 2 are in fact given by a complex conjugate pair. In fact, this A1 and A2 satisfy two things. This A1 and A2 are such so that the initial values of I and Vc are satisfied by this response. So, what we have to really see is that this A1 and A2 are such that I is equal to F1 plus F2 satisfies I0 at t is equal to 0. So, your A has to be chosen in that fashion. Also, if you take out the response of Vc, in fact Vc is nothing but the derivative of the current. At time t is equal to 0, the values of A1 and A2 should be such that Vc0 is also satisfied. That is, Vc evaluated at time t is equal to 0 should equal to the initial condition which you have given. So, if you give an initial condition which is not 0, you should ensure that A1 and A2 should be such that both these initial conditions are satisfied. Even if it is 0, you should ensure this. So, what you find here is that this e raised to lambda 1 and 2 are in fact defined by this. Your final response, if you assume that everything is real here, A1 and A2, lambda 1 and lambda 2 are a complex conjugate pair, and it turns out that A1 and A2 also will turn out to be complex conjugate pair. So, if everything is real in this circuit, the final response, both the natural and forced response, will come out to be real. So, what you effectively see is that because of the fact that this is a complex number, you will find that the combination of these two lambda 1 and lambda 2, which are complex conjugate pairs, will result in fact in a damped sinusoid, because this is like sigma plus or minus j omega n. Now, if you have got sigma plus or minus j omega n is what you call the natural frequency of the circuit. What you will find is that your response is in fact e raised to lambda 1 t will be equal to e raised to sigma plus j omega n t, and e raised to lambda 2 t is equal to e raised to sigma minus j omega n t. Now, I will not do the math, but one of the interesting points which you would be able to infer quite easily without actually working it out, or you can see that it seems intuitively satisfied, but we will not work it out in detail, is that since sin omega t omega n t is equal to e raised to j omega n t minus e raised to minus j omega n t by j omega and by 2j, sorry, and cos omega n t, this is a well known identity. By 2, what we because these two appear as complex conjugate pairs, and in fact the initial conditions are real, you will in fact find that A1 t plus A2 lambda 2 t will come out to be some A e raised to sigma t sin omega n t plus gamma. So, you will have in fact instead of you will in fact have a natural response which is of oscillatory nature, okay. And of course, if sigma is negative, which it is in this case, it will be a damped sinusoidal nature. So, remember this is only about the forced the natural response. Remember, your response of current and of course voltage Vc is equal to dVc by dt is equal to 1 by C into I. So, the Vc can be obtained by integrating whatever response you have got. So, the response of the inductor current and the voltage Vc is given by a natural and a steady state response component and a forced response component. If your input is k e raised to st plus alpha, the forced or rather I should say the steady state response is given by k e raised to st plus alpha upon r plus this, and the natural response is given this. The values of A1 and A2 and equivalently A and gamma are such that the initial conditions of the circuit are satisfied. There are two initial conditions here, that of the inductor current and of the capacitor voltage, which are of course associated with the differential equations of the circuit. So, your final response is, if your input is k e raised to st plus alpha, your response of current and in fact also of voltage, the nature of response would be similar. The current would be k e raised to st plus alpha divided by r plus 1 upon sc plus sl, and the natural response would be given by E sin omega n t plus gamma into e raised to sigma t. So, this is the final response which you get. Of course, if you want to get the response of V c, it will be the integration of this. So, what you will actually get is the response of this will be 1 upon s of this. So, we will get the force response will be, you can just verify this I am not proving here, is nothing but 1 over s into r plus 1 over s c. In fact, it is not only the integration, but you have to also scale it by c, because the current plus some a dash sin omega n t plus gamma dash into e raised to sigma t. This a and gamma dash of course may be different here. So, what you find here is a kind of a response which can be directly obtained, and the thing is that if you put s is equal to 0, you will find that the response turns out to be, for current, the steady state response is 0, because this tends to infinity here. If you make put s is equal to 0 or tending to 0 here, you will find that V c will be equal to the input voltage, because this into this will tend to 1, okay, if you put limit s tending to 0. So, that actually gives you directly the DC steady state if you plug in s is equal to 0. If you want to actually find out what happens if your input is sinusoidal, so suppose I want to find out what in case my input is sinusoidal, that is V is not, so if V is k times sin omega t plus alpha. Suppose your input is this. So, how do you actually solve this problem? It is not difficult to do it. All you do is actually plug in s is equal to j omega here. So, you plug in s is equal to j omega L here. So, this component, at least the steady state component, can be quite easily found out. It is k e raised to j omega t plus alpha upon r plus 1 upon j omega c plus j omega L. So, what you will get is, one thing is the scaling factor and a phase shift, because this is a complex number. So, this will be equal to k, this is equal to, I am talking of this is equal to k into e raised to j omega t plus alpha into e raised to minus j phi divided by root of, now you will get, unlike the previous case for an RL circuit, now you will get in fact omega L minus 1 upon omega c square, and this phi is of course the angle, that is the tan inverse this imaginary component divided by r. So, phi will come out to be tan inverse omega L omega L minus 1 upon omega c divided by r. So, in fact, this entire thing. So, what you see is that you can get the response. So, what is the final response of the current, steady state response of the current? So, if you plug in s is equal to j omega, this is the response you get. So, if you give actually a sinusoidal input which is V is equal to k sin omega t plus alpha, the response will be k, the current response will be k upon root of r square plus omega L minus 1 upon omega c square into e raised to minus j phi, where phi is equal to tan inverse omega L minus 1 upon omega c divided by r. And in fact, this will be not e raised to minus j phi, because now we will get e raised to omega t plus alpha minus phi. So, this is in fact what your response is going to be. So, if you have got sinusoidal inputs or DC, one can actually infer the response quite easily using complex numbers. Although this particular response is obtained when your input is this is the response. But it turns out that if you infer this, if you get this response, you can easily infer what is the response for sin omega t plus alpha. It is simply you use the same scaling factors and the phase shifts. So, directly you get this response. This is called the sinusoidal steady state response. But remember one thing quite clearly, that your final response is this plus E sin omega n t plus gamma into e raised to sigma t. Now, what is, so you have to really distinguish right now two things. This is the input voltage and this is the frequency of the input voltage, which in this case we are considering a sinusoidal voltage with frequency omega. The natural response of this circuit is in fact also a sinusoid. Well, it is a damped sinusoid with frequency omega n, where sigma and omega n are obtained as roots of this. So, interestingly, by this simple analysis of trying to obtain the response for the circuit for a generic input e raised to st plus alpha, there are two things you can take out. One is, quite conveniently, you can get the sinusoidal steady state response, where this omega here corresponds to the frequency of the input, whereas the natural response is in this case sinusoidal, a damped sinusoid, because you get complex roots of this equation. So, contrast this with the RL circuit, where the natural response was e raised to minus r by L into t. So, the natural response of this circuit is in fact a damped sinusoid. The damping depends on the value of sigma, which is actually negative. An interesting thing is, whenever you have got a resistance which is positive, of course it is a positive value for all conductors, the thing is that your natural response as t tends to infinity becomes 0. That is, the natural response eventually dies out, this dies out, and what you are left with the final, the sinusoidal steady state response. So, this is an interesting aspect about sinusoidal steady state and natural response of circuits. So, in fact, you can quite easily obtain the natural response of any circuit containing R, L and C's in this way. You can also get the sinusoidal steady state response. Remember that you can get the DC response also. You plug in S is equal to 0, you get the DC response. In case you have got more than one sinusoidal input, the sinusoidal steady state will consist of not only this, but the response to the other sinusoidal inputs as well. So, if you have got more than one sinusoidal input of different frequencies, you have to evaluate this for each frequency separately and superimpose the response as far as the sinusoidal steady state goes. The natural response there are complicated formulae which will give you the values of A and gamma here, but the important thing to note here is that the natural response is such that it also satisfies the condition that if you plug in t is equal to 0 and plug t is equal to 0 here, you will find that the initial condition I0 is satisfied. That is, if you plug in t is equal to 0 to the general response, which consists of both the sinusoidal steady state as well as the natural response, you will find that at t is equal to 0, I will be equal to IL0. Okay. So, that is the way you can, without any complicated mathematics, arrive at A and gamma here. Okay. In fact, in this circuit there are two initial conditions and both have to be satisfied. So, the solution for Vc also has to satisfy this the initial condition. So, the initial condition of Vc also has to be satisfied. Now, what we one must remember here again is that if I give you a circuit and I ask you to take out its response, please remember that the natural response may be present. In fact, of course, you can tune the instant of switching, or in the case of the RL circuit, we showed that in the last lecture, that you could tune the value instant of switching so that the natural response is minimal. In this case, you could, for example, have a set of initial conditions on Vc and also tune the instant of switching both. If you do them both, you can actually get a situation where A becomes equal to 0. In that case, you will directly go into sinusoidal steady state. So, such a thing can happen, but in the most general situation where you have got arbitrarily initial conditions, or you switch on at an arbitrary instant with respect to the input waveform, you will find that there is always a natural response and a transient response. So, what we will do is quickly look at the an experimental demonstration of RLC, but before we do that, let us first just have a quick question. I have a quick question for you. So, if you, for example, consider this circuit here, remember that this circuit has got a natural response with a frequency which is approximately 200 hertz. In fact, let me just show it to you again. We actually evaluated the natural response. So, sigma and omega n, remember now we have to distinguish between two things, omega n and this is the natural frequency, this is in radian per second, this comes out to be 200 hertz, and the real part is minus 78. So, since it is negative, we have got a decaying natural response. Now, in case you have got a sinusoidal source, the source also has got a frequency, and so your steady state sinusoidal response in fact will contain a frequency which is equal to the sinusoidal, the source frequency, the frequency of the sinusoidal source. The natural response will get damped out. So, this 200 hertz oscillation which you see because of the natural response will eventually die out. So, the question which I would like to ask you here is, suppose I give you this circuit and the initial current is 0 ampere and capacitor voltage is 0 volts and the input voltage is 10 times 10 sine omega t, which is a 50 hertz waveform, for a 50 hertz waveform into t. So, what is the response of IL and T? So, I have given you 4 options here. The one on the top in fact is Vc, and the second, we have 4 options. In each there are 2 graphs, one is of Vc and IL. Remember that if you look at the circuit, the current which is flowing through the inductor is also flowing through the capacitor, and you know that the capacitor Vc voltage satisfies the relationship C dVc by dt is equal to the current flowing through it, but the current flowing through it is also the inductor current. So, in sinusoidal steady state, you will find that if current the current and voltage will have a 90-degree phase shift, that is the current through the capacitor will be 90 degrees leading the voltage through the current flowing through it, because C dVc by dt is equal to I, and this is satisfied not only during transients, but also during the steady state. So, in steady state, since the natural response will die down, we are just left with the sinusoidal steady state response. So, if you take the derivative of say sin omega t, you will get cos omega t. Okay. But of course, we do not know what the current is yet, rather we could find out by solving this circuit what is the current, but the fact remains that the voltage in the capacitor across the capacitor lags the current through it, and therefore, if one is asked the question which of these 4 options are correct, one is tempted to eliminate, or rather one should eliminate the kind of response, sinusoidal steady state response, in which the voltage leads the current. So, which are the responses in which the voltage leads the current? Option B, the voltage V leads the current in steady state, after the natural transient dies down. So, this B option has to be eliminated because it really does not give you the correct steady state phase relationship between I and V. So, B is eliminated. What you see in these 4 responses is also the first response, if you notice, the voltage at the beginning we see is minus 10 at time t is equal to 0. This does not satisfy the initial condition which you have mentioned earlier. So, this cannot be in fact the correct response. So, we have the A and B are in fact wrong directly, we can say. If you look at C as well, you will find that the current is not exactly 0, it is slightly above 0, the voltage is above 0 and even the current is not at 0, and this does not satisfy the initial condition. So, this also cannot be the correct response. The correct response is the one given in D. And what you notice here is that in sinusoidal steady state, the current tends to lead the voltage across the capacitor, which is of course consistent with the relationship between voltage and current. The second thing which you notice here is that the initial conditions are satisfied. In fact, the natural transient in a way adjusts itself. You can look at it that way. The natural transient, which is the entire response is the sinusoidal steady state plus the natural response. The natural response in some ways has adjusted itself so that the initial conditions are satisfied. So, even without actually doing a very detailed solution, we can actually obtain the response. What we notice another thing is the natural response dies down, you will find that what is this, and this natural response is oscillatory. In the RL circuit it was an exponentially decaying offset, but here you see it is a decaying sinusoid, and this frequency is 200 hertz. So, remember that there are 2 frequencies here. One is the natural frequency of oscillation, which is a damped sinusoidal oscillation, that is of 200 hertz and it is damped out, and one is the steady state response, the sinusoidal steady state response. So, answer D is correct. There are few takeaways here. There is a distinction between a natural response and a steady state response. The natural response will display properties of the roots of what is known as the characteristic equation. In this case it was S square LC plus SCR plus 1 is equal to 0. The roots of that would give you the characteristic equation. The roots of that would give you the nature of the natural response. In this case the roots are a complex pair with negative real parts, which indicates the presence of a damped oscillation. The damped oscillation appears in the beginning so as to satisfy the initial conditions. You can actually get quite rigorous solutions in more complicated circuits as well as this one for the amplitude of the natural transient. But one simple thing which you can remember is that the natural frequency always, natural response always adjusts in such a way that the initial conditions are satisfied. In this case the initial conditions was 0, 0. In case your initial condition was not 0 of the voltage or the current, then of course all what you need to check, rather what you need to check, not all what you need to check, but what you need to check first is that the initial conditions are satisfied and the sinusoidal steady state response is also satisfied. In case you had 50 hertz and 50 hertz input, the input was not only a sinusoid of 50 hertz, but it contained a 150 hertz component as well, then your final response would contain the natural transient plus the response, sinusoidal response corresponding to 50 hertz, as well as the sinusoidal steady state response corresponding to 150 hertz. So, this is the kind of things you can expect when you talk of natural responses. Now, one interesting point when we are talking of transients in circuits is the concept or rather modeling idea where we can do a kind of decoupled analysis of fast and slow transients. But before we do this, let us quickly do an experiment of this RLC subjected to both a DC and AC transient. So, we will just quickly show you the experimental demonstration of this. So, in this case, first thing is we will have a DC source, which is a battery which has got a voltage of 9.35, and what we will do is subject it, this battery is connected by a switch to a resistance which is 10 ohm, which of course the resistance will be slightly higher than this, because the winding resistance of this inductor also will get added on to it. And you have a capacitor of 10 microfarad, that is. So, essentially we have got the same circuit as the one we studied some time back, and what is going to happen is now he is going to switch this on and measure this using a voltage and current probe, the voltage across the capacitor or the switch. What he is going to do is measure the voltage across the switch, not across the switch, essentially the voltage across the RLC. Yeah. So, this is not the same as the voltage across the capacitor. So, what you will notice of course is, as soon as you switch on the battery, you will find that you have got this oscillatory transient, but the DC voltage which is applied to this RLC circuit also oscillates. The reason being that the current drawn is more than what the battery can, as you load the battery voltage drops. In fact, the kind of currents which are drawn result in a very perceptible drop in the voltage of the battery. So, it is not exactly a DC, but it is like a DC, but not exactly a DC. Yeah, and this is the response of the circuit, and of course, one or two things you can infer from this is that is the frequency matching or not, and one of in this example, unfortunately the scales are not very clear, but in case you do this experiment, you just check whether the frequency matches the theoretical frequency which you get by theoretical analysis. You are likely to get some deviation. The reason is of course that this resistance of the winding has not been considered here. In fact, in the theoretical analysis we consider 10 ohm, but here the resistance will be slightly more than that, and therefore, you will find in fact that the frequency, natural frequency will not match exactly to that. So, this is one interesting thing. As before we saw that when you switch on this circuit, it is not a very smooth or it is not a step, because probably because of two reasons. That is because one, the switch is not a perfect switch, it does not switch instantaneously on. There may be a bit of a what you call bouncing, in the sense that it does not make a perfect contact instantaneously. And the second thing is of course they are parasitics, because of the fact that this circuit is forming a loop. You have got parasitic inductances and capacitances, which we discussed in a few classes before this. Now, if you put AC voltage, so this is the second thing we are going to see. What you notice here is we can increase the voltage here, and one of the things of course is this capacitor. If you have done this experiment, the capacitor would be charged at 9.35 volt. So, you need to discharge it and get it back to 0 if you want to start from 0 initial conditions. So, that is one important thing you should remember. If you are doing this experiment right after you did the previous experiment, the capacitor would still have some charge. Eventually, it would discharge through parasitic resistances across its terminals, but what you need to do is to discharge this capacitor if you want to start from 0 initial conditions. Yeah. So, we will have a 60 millihenry inductor as before. There is nothing really new here. This is a 10 microfarad capacitor. Actually, it is a 6 microfarad and 4 microfarads connected in parallel. Yeah. So, we will give a step input. In fact, to avoid nonlinearity, we will not give a very large nonlinearity in the inductor. What we will do is we will actually apply a small voltage. We are using 30 volts RMS. In this experiment. Yeah. So, the moment you give a step change, yeah. So, what you will notice here, if you discount the initial non-ideality due to the switch, here also you will find that you have got the natural response which dies down and you kind of reach the sinusoidal steady state. One of the interesting things you observe in this experiment is that the current waveform is not really sinusoidal, and possibly the reason for that, even in steady state, that is one of the reasons of that could be the fact that the voltage which is applied itself is not sinusoidal. So, the voltage which you are applying here is not a good sine wave, and what we get as a result in the sinusoidal steady state is not a very neat sine wave. The sine wave also has got some harmonic components. So, although it is periodic, it does seem to contain harmonic components, and that is most likely due to the fact that this voltage also contains harmonics. So, you get a sinusoidal steady state response to a voltage which has not only one frequency component, but several. Yeah. So, what we will do next is we will switch off this circuit and then discharge the capacitor. So, that is what he has done, is discharge the capacitor, and we will redo this experiment. But now what we will do is we will just since we are kind of almost randomly switching it on, that is what he is doing now. He switched it on and he has triggered the oscilloscope, and what you notice is that now the natural response starts at a different point. So, what you find is that the natural response looks a bit different from the one before this. The natural response here is in fact slightly different from the one we considered before, because the instant of switching is slightly changed. Now, this is of course a random thing. You can keep on doing this experiment and you will find that the nature of the natural response changes, but the sinusoidal nature, steady state nature does not change. In fact, in this circuit you will find is mostly capacitive, that is the omega 1 upon omega c component dominates over the omega L component. So, what you find is the phi in steady state, which is tan inverse omega L minus 1 upon omega c by r, comes out to be minus 90 degrees. So, in fact, there is a phase lead for the current. Okay. So, that is what you see here, and of course, here again one more thing we notice is that the input voltage and therefore, even the steady state current is not purely a sinusoid of one frequency. There seem to be many frequencies in it. It is not looking like a, although periodic, it is not sinusoidal, and that is because the input voltage source itself is not sinusoidal. Yeah. So, this is another instant where now the switching has happened somewhere else. So, you do see the natural response slightly changed, okay. But again the sinusoidal response does not change, even though neither the magnitude nor the phase shift. So, this is not surprising. So, with this we come to the end of this this experiment. Now, there is one interesting point which I wanted to discuss here, which is a very important modeling principle as well, is the concept of slow and fast transients. In fact, even before we do this, one of the things you can try at home is to try to actually numerically integrate, we try to get analytical solutions and also did experimentation, but you can also use a computer simulation that is using a numerical method to integrate this response. Yeah, so you can in fact use Euler method as was discussed in the previous lecture. So, you can actually numerically integrate the system as well. So, we will not actually do the numerical integration, but we will just show you how it looks like, the program looks like. So, this is a you can give the value of R, L and C and you can play around with it of course. You use a time step of 10 microseconds which we hope will be adequate for numerically simulating the system, and of course, here you have got two sets of differential equations, one for the voltage dVc C dVc by dt is equal to I, and for the current you have got the equation which we had written down a bit earlier. So, you have got two equations which you can numerically integrate, and that is what is shown there in the program here. So, if you come down here, you will find that this is how you and you can plot it. Yeah. So, this is what the response you get. This is a numerical integration and we have plotted the response, and this is somewhat what we got in our experiment as well as from our theoretical analysis. So, this is something interesting, and I encourage all of you all to just try out these simple things. This program has been written on Scilab. So, so as I was discussing some time ago, that we will just look at one interesting feature and then conclude this lecture, and that is relating to what are known as fast and slow transients. An interesting thing about modeling is you know, in case you have got a system in which they are both forced slow and fast transients, like the one you will see on your screen. So, for example, there is a system which has got a resistor of you know 0.1 ohm and 10 millihenry, and there is a large inductance of 1 henry and a capacitor of 10 microfarad, I am sorry 100 microfarad. And if you look at if this system, you will have in fact 3 differential equations. You could choose you know the differential equations which can be in the current through this inductor 1, and then the current through the inductor 2, and the voltage across this capacitor. So, you using KVL and KCL, the KVL equations, there are 2 loops here. One is this one there, what is being shown. The second loop is between this. So, there is a second equation. So, there are 2 differential equations there, and the third differential equation comes because when you apply the nodal you know Kirchhoff current law to this node. So, you will actually get 3 differential equations, and again if you assume the input to be k e raised to st plus alpha, you can actually get the steady state response in the manner I showed you. In fact, in this circuit the natural response can be obtained by setting the denominator of this the you know the expression which you obtain for the steady state response to 0. So, in case in this equation, in fact if you got RLC here, remember that once you turn on the switch, in fact it is not a sinusoid, it is a step voltage V, and this, and then you have got this SL and this. So, for example, if you want to take out the current through this inductor, what you need to do is, this is R, this is SL 1 upon SC, this this is SL and this is 1 upon SC, and the current simply comes out in case the voltage is e raised to k e raised to st plus alpha. If V is equal to this as a function of time, then the current has got components which are natural transient, the steady state component. The steady state component comes out to be k e raised to st plus alpha upon this. So, this is R plus SL1 and this SL2. So, you have got R plus SL1 plus the parallel combination of this. So, this is SL2 into 1 upon SC upon SL2 plus 1 upon SC. So, actually the steady state, in case this is DC, of course, the current in steady state will be obtained by putting S is equal to 0 here, and if you put S is equal to 0 in this circuit, you will find that the current comes out to be V by R. And the other thing which you also can infer is that the roots of this, when you set this to 0, will give you an indication of the nature of the natural response. In fact, without actually working it out, let me tell you, for these values of R, L1, L2 and C, we will get two, one negative real root. So, we will have one negative real root, and we will have also a complex pair. So, there are three roots of this equation. This is equal to 0 and this will be sigma plus or minus j omega. This is a small number, and whereas these omega and sigma are relatively larger numbers. So, what you get is, in fact, the natural response will consist of terms like e raised to sigma t and e raised to sigma 1 t and e raised to sine omega, I will call this omega n, sorry, omega n t plus gamma. So, these are the kind of natural response you will get. So, if you have a DC source, you will get the steady state response for current to be V by R, and also you will get a natural response. So, let us just concentrate right now on the natural response. So, if you go to this circuit which is shown here again, suppose I give a step change to this. Now, one interesting thing is, because in this circuit the natural response consists of a damped sinusoid of very large, which has got a large negative real part, that is the rate of damping of that oscillation is very fast, and also the oscillation frequency is quite high. So, if you look at the natural response I mentioned some time back, sigma 1 and sigma plus or minus j omega n, the omega n in the natural response is quite high, and therefore, if you actually give a step change, you will actually be able to see these natural responses. One is the damped oscillation and also a slow exponential decay. So, both these things are seen. So, a damped oscillation and a slow exponential decay. But the characteristic feature of this circuit is that the natural frequencies are in fact quite well separated, in the sense that this decay of this sinusoid and also its frequency is very fast, whereas the other exponential component dies down very slowly, or you see that the rate of change is very slow. So, in fact, you can study this example in two ways. One is that when we are studying faster transients for a short duration, the current through the large inductor is virtually unchanged. So, while this oscillation, fast oscillation is taking place, since this is a very large inductor does not allow the current through it to change very fast. So, you can assume for all practical purposes that when you switch on this switch, the current through this inductor is practically unchanged, and if you assume that, then a model which is valid for a very short time after the switch is switched on is this. So, this is called a fast transient short term model. So, if you look at this, the response of this is actually, whereas the actual response is shown here on the left hand side, it is expanded from the kind of response which I showed you in the first figure. This part is expanded. If you take instead of the original circuit, for which the left hand side response, the response is what we show on the left hand side, and actually get the response of the approximate model, you will find that the approximate model at least captures some features quite correctly. You will find that the frequency of this response of this approximate circuit, in which you have neglected the large inductor, is almost the same as what you get for this original circuit. Of course, there are some differences in scaling here. Conversely, if I want to study only the slow transients, there is a slow transient. If you want to just study the slow transient, we can also make another approximation that these if the changes are very slow, then these L di by dt and C dV dt of these two small components, small in the sense of the values of L and C are small, the values of C dV by dt and L di by dt for this inductor and capacitor are very small. So, in that case we can assume that this inductor practically has no voltage across it when the rates of change are very slow, and the capacitor has practically no current flowing through it when the rates of change are very slow. So, in that case we get a simplified model of RL, and what we really see the response, the original response is what you see on a left hand side, the detailed model, whereas if you take an approximate model, this is what you get. Now, what is the inference? Of course, the approximate model does not give you exactly the response which is given on the left hand side, but what you see is that it captures the slow transient quite well. So, this is an important modeling aspect, that in case you are interested in transients which are relatively slow changing, you can neglect the dynamics associated with very small components or components whose inductances and capacitances are very small. So, in fact, we have already done this. I mentioned some time back that anytime you make a circuit which has got a loop, there is in fact, whenever a current flows, a magnetic flux through the loop, and this causes a kind of inductive effect just simply because of the fact that there is a loop. But we very often neglect this feature and call it parasitic. Similarly, the wires which are used to interconnect all the elements, they themselves have got some charge resident on them, and which causes an electrical field, and therefore, you have got some capacitive effects just because of the wires being separated from each other in a kind of a insulated medium. So, both capacitive and inductive effects are there, which we have neglected simply because of the construction of the circuit. So there are these parasitic capacitors and inductances which are kind of distributed around this. Even the inductor, as we saw, could be modeled in the second or third lecture. We saw that you could model a real life inductor as L in parallel with a C, but that C is extremely small. So, its effects are seen only in a very short time duration, or when you excite it with you try to excite its response at very high frequencies. So, if your interest, your region of interest or your transients of interest are slow, often you can neglect these parasitics, and that is what we have done when we considered this lumped RLC kind of transients in this previous lecture. So, we do not consider the parasitic effects. So, for example, this circuit which we saw some time back, the detailed circuit, you could consider this L and C as some kind of parasitics which exist in the circuit. Neglecting them means you will actually get a small error in the response, but this small error in the response is usually lasts for a very short while and is associated with very fast transients. So, if you take a approximate model, this is what you will get, whereas the actual detailed model gives you this. Not much of an error really, if you are really interested in the slow transients. Is that okay? So, with this very important principle of modeling, where you can actually make modeling simplifications depending on what transients are of your interest or what is the kind of frequency range in which you are working, you can make modeling simplifications, and we implicitly do this all the time. This is something will be kind of a recurring theme in what we are going to do, although we may not mention it all the time. So, with this we end today's lecture.